You know that feeling when you're trying to do something that feels, well, impossible, like lifting something super heavy, and then you grab a simple tool and suddenly the job's easy. That's not magic, my friends, that's physics. Today, we're going to unlock the science behind one of the simplest but most powerful tools ever invented, the lever. And you're about to see it's less about your muscle and a whole lot more about math. Okay, so here's our game plan. We're going to start with the absolute basics. What in the world is a lever? Then we'll dive into the different types, the actual science that makes them work, and yeah, we'll even do a little bit of math to figure out their power. To wrap it all up, we'll talk about something called the principle of moments, which is all about creating perfect balance. So let's just kick things off with a question that really gets to the core of this whole thing. How can you put in less effort but get way more done? Well, the answer is a concept people have been using for thousands of years to build, well, everything from the pyramids to modern skyscrapers. Just look at these. Over on the left, you've got one person about to move this huge boulder with just a stick. And on the right, a bottle cap getting popped off with just a little flick of the wrist. They look totally different, right? But they share the exact same secret. A small, focused effort that creates a massive result. That, right there, is the power of leverage. And that leads us right into our first big topic. What exactly is this simple machine that gives us such a huge advantage? Let's break it down. At the end of the day, a lever is really just a stiff bar that pivots or turns around a fixed point. That's it. The real magic is in how that simple little setup multiplies your force, making it one of the most important tools in, well, pretty much everything. To really get how any lever works, you just need to know its three basic parts. First up, you've got the effort. That's the push or pull you put in. Then you've got the load. That's the thing you're trying to move. And finally, the most important part, the fulcrum. That's the pivot point that everything else turns on. Let's make this real. Imagine you're using a spoon to pry open a can of paint. Think about it. Your hand pushing down on the spoon, that's the effort. The really stubborn lid you're trying to lift up, that's the load. And the rim of the can where the spoon is resting and pivoting, that's your fulcrum. See? Effort, load, fulcrum. They are literally everywhere. Now here's where it gets really interesting. It turns out that the way you arrange these three parts, the effort, load, and fulcrum, totally changes how the lever works. And this gives us three different classes of levers. Let's start with class 1. This is the one you probably think of first, right? The classic seesaw. The rule is super simple. The fulcrum is always sitting in the middle between where you put the effort and where the load is. This setup is awesome because it can multiply your force and it changes the direction. You push down and the load goes up. Think about a pair of scissors or pliers. That pin in the middle where they pivot, that's the fulcrum. Your hands squeezing them, that's the effort. And whatever you're trying to cut or grab, that's the load. Effort on one side, fulcrum in the middle, load on the other. That's a classic class 1 lever. All right, next up, the class 2 lever. For this one, the arrangement gets shuffled around. This time, the load is in the middle, sandwiched between the fulcrum and the effort. And the big advantage here is that you always get a force multiplier. You're guaranteed to use less effort to move a bigger load. A wheelbarrow is the perfect example. The axle of the wheel, that's your fulcrum. All the heavy stuff you're carrying inside, that's the load, right in the middle. And you, lifting up the handles at the very end, that's the effort. A nutcracker works the exact same way. Hinge is the fulcrum, nut is the load, your hand is the effort. And that brings us to our last one, the class 3 lever. Here, the setup flips one more time. Now, the effort is what's in the middle, between the fulcrum and the load. Now, I'll admit, this one can feel a little backwards at first. A fishing rod is a great example. The butt of the rod pressed against you, that's the fulcrum. The fish way out at the end of the line is the load, and your other hand lifting the rod in the middle, that's the effort. Now, you're probably thinking you're not multiplying force here. Actually, you're using more effort than the load, so why do it? Well, it's a trade-off. A small movement of your hand creates a huge, fast movement at the end of the rod. You trade force for speed and range of motion. Tongs and tweezers do the same thing. So, we know what levers are, and we know the three different types. But what's the actual science? What's the secret sauce that gives them their power? Well, that brings us to a really key idea in physics, the moment of force. Moment of force. Sounds a little complicated, right? But it's not. It's really just a fancy technical name for turning power. Seriously, When you push on a door to open it, you're creating a moment of force around the hinges. It's this turning effect that levers are so good at using. And the best part, we can actually calculate this turning power, and the formula is super simple. The moment is just the force multiplied by the distance. Now, the force is measured in newtons, and the distance from the pivot point has to be in meters. That's the key. Just remember, force times distance. That's all it is.
Okay, theory is great, but now that we have the formula, let's get our hands dirty and actually put it to the test with a real example. Let's see how this goes from just an idea to a calculation you can do yourself. All right, let's go back to our trusty spoon and can lid. Imagine you're pushing down on the end of that spoon with a force of 10 newtons, and let's say the distance from where your hand is pushing to that pivot point on the can's rim is 15 centimeters. So what's the moment of force? Okay, let's walk through this together, step by step. Step 1, we identify our force. That's 10 newtons. Easy enough. Step 2, we identify the distance. It's 15 centimeters, but hang on. Remember what I said? The formula needs the distance to be in meters. This is the one place people always get tripped up. So we have to convert 15 centimeters into 0.15 meters. Now for step 3, the easy part. We just multiply those two numbers together. 10 newtons times 0.15 meters. And boom, our answer is 1.5 Newton meters. And that number, that 1.5, that's it. That's the amount of turning power you're applying to that stubborn lid. It's the actual precise measure of the advantage that lever is giving you. Pretty cool, right? All right, we are on the home stretch now. For our last section, let's look at what happens when a lever isn't moving at all, but is just perfectly balanced. And this is all explained by something called the principle of moments. And the principle itself is actually really simple. For a lever to be perfectly balanced, like a seesaw that's not moving, the turning power on one side has to exactly cancel out the turning power on the other side. This means the clockwise turning effect has to equal the anti-clockwise turning effect. Or, to put it another way, the load multiplied by its distance from the middle has to equal the effort multiplied by its distance from the middle. And there you have it. From what a lever is, to the different classes, to the physics that makes them tick, you now get the secret power of levers. So the question for you is, now that you know what you're looking for, how many first, second, and third class levers are you going to spot in the world around you today? I bet you'll be surprised.